Alright, so we're talking about transformation. So before now, like in algebra 2, you talked about like each function individually. You looked at the graphs of x squared. You looked at the graphs of your square roots. Now we're going to kind of look at them more generally and say, oh hey, hopefully we notice like each of these follows the same pattern. My transformations are the same no matter what my function is. Okay? So we're going to look at more general types of rules that will work for any function. Before we get into that, we do need to look at our last type of function that we have, okay, which is our greatest integer function. Now, if we haven't seen this function before, it's all right. It doesn't really come up a whole lot before now, so if you haven't seen it, that's okay. We can look over it together now. Now, the other term that this is called is our step function. Hopefully, by looking at our graph, we can kind of see why it's called a step function. Yes, they kind of look like little steps. Okay. So a step function is going to be a function that increases by a specific interval or step. So our most common step function is the greatest integer function. So your greatest integer function, so it looks very similar to like our normal square bracket that we use for our interval notation, but then you draw an extra line. And that is what you're going to write at the top of your little square for your information. And then on the left side, you can draw your graph. So hopefully we notice that our domain is still all real numbers. So negative infinity to infinity. Now what's our range for this function? Can it be any y value? No. What type of y values are we getting? Integers. So basically, there's not really a nice way to write this besides to say y such that y is an integer. So we can only get whole numbers, positive or negative, for our outputs or our y values. Now, do we have a y-intercept? Yes. What is it? 0, 0? Now, what about our x-intercept? Do I have 1? Do I have 2? Do I have more than 2? I have infinite. So notice, right? All of these points right here from 0 to 1 are along my x-axis. Agreed? Which means that all of these points, okay, are going to be x-intercepts. So that would be from 0 to 1. Notice that I'm not including 1 because 1 is an open circle. But how many numbers are there in between 0 and 1? A lot, an infinite amount, right? Because I can always find a smaller fraction. Or a smaller decimal. So that's just how we're going to write it, because we don't want to list it all out. Now, to evaluate this function, we kind of need to write out what the definition is. So like this is what's on your little foldable. Over here, you can put this in your notes, or if you just want to remember it, that's fine. But our greatest integer function is the greatest integer that is less than or equal to or whatever you're plugging into the inside. So we're going to look at an example of evaluating here in just a second, and that's where that definition is going to be helpful. Questions so far? Yes.
So it's constant, it's not increasing or decreasing.
So like, it's a weird function. Yes, so technically it's constant between each of those intervals, right? But the overall function is increasing. There's not really a nice way to write that, so that's why we don't really usually describe its increasing, decreasing constantness, if that makes sense. I don't mind doing that, just a little bit more fun. Alright, so on our examples, now we're actually going to evaluate. So remember, to evaluate just means to plug in. Okay, so I'm evaluating at these three different numbers. So when I'm looking at my order of operations, what comes first? Order of operations. What comes first? Parentheses. Okay, technically it should be grouping symbols, right? Because parentheses is what you're all used to seeing, but it includes any type of grouping symbol. So we're going to include our greatest integer function as a grouping symbol. So we have to do that function first, and then add, subtract, multiply, divide, whatever it is the other stuff is. So again, we're going to go back to that definition that I talked about. So what is the greatest integer that is less than or equal to -1? Do we agree with that? Yeah. So what is the biggest integer, so integer being whole number, that is less than or equal to -1? -1, because -1 is already what? Equal to -1, and -1 is an integer. So anytime that you plug an integer into your greatest integer function, you're just going to get out that integer. So like on our second one, and then I just added 1. But like on our second one, when we are evaluating at 2, what kind of number is 2? It's also an integer, so what am I going to get out when I evaluate the greatest integer function of 2? Just 2. So our overall answer would be 3. Are we okay with both of those? Does that make sense? And like I said, that would be true for whatever integer you plug in. What becomes a little bit different is when we start plugging in fractions or decimals. So here we have f of 3/2. So if, say, we wrote out a number line, I think that's a little bit helpful sometimes. Where on my number line does 3/2 live? Between 1 and 2. Okay? So we're basically trying to pick the biggest whole number that is smaller than. So on a number line, smaller than means in which direction? To the left. Okay? So notice I have a bunch of integers that are smaller than 3/2. But I have to pick the biggest of all of those, which would be what? 1. So the greatest integer function of 3/2 would be 1. Now, they don't ask us to find it, but I want us to practice with it. If I plugged in a -3/2, be careful. Where does -3/2 live on our number line? Okay, so what is the biggest integer that is less than or equal to -3/2? -2. Because again, it still has to be to the left, which would be -2. Which is why I kind of like using the number line, because it's easier to see that. Because sometimes with the negative numbers we forget, right? Bless you. And that our -2 is smaller than, right, our -1. Questions on that? So far, so good? Okay. So that's our greatest integer function. Mostly, like, if I ask you something about it, like on a test, it's mostly going to be evaluating it or finding the domain and range. I'm not really going to ask you to graph those on your own, but I do want you to know kind of what they look like, to where if you saw one, you would be able to say, oh, hey, that's the greatest integer function. Does that make sense? Okay. But now, let's start talking about our transformations. So, remember, hopefully, back to Algebra 2 and Algebra 1 when you started looking at graphing for the first time. Your first type of transformation are shifts, meaning going up and down, or left and right. And like I said, we're going to kind of look at these for all functions, not a specific function. So we're going to start with different types of parent functions, which is why it's good to have that list of all of the different types of parent functions that we could use. And then we're going to look at the different transformations we can do with whatever parent function you're given. They work the same way. So remember that if we add or subtract something on the outside of a function, okay, it's going to move it up or down. If we add or subtract something on the inside of a function, it moves it left and right. But remember that it moves it the opposite direction of your sign. Can anyone tell me why? Yes, no, maybe? Yeah, so remember that when we're talking about moving left or right, we're talking about our x-axis, right? So like if I set whatever's on the inside, so say x plus 2 equal to 0, I would have to undo it by doing the opposite, which would be subtracting. Yes? Which is why it moves it the opposite direction of whatever your sign is. That was how people still writing. Oh, wait a second. Didn't look at it good. Alright, so let's look at an example. So, it tells us that we are starting with the graph f of x equals x cubed, and then we're going to use that graph to sketch the other two graphs that it gives us. So, we need to probably start by reminding ourselves, what does the graph of f of x equals x cubed look like? So we should have our little foldable. We can open it up if we need to. What is it?
It starts at the origin.
Huh?
Goes, one line goes like really vertical pretty fast.
Okay. So we go through 1, 1, right?
Yeah.
And it kind of looks like half of a parabola, but facing upward. And then the other side goes through -1, -1. And basically it's the other half of a parabola, but facing downwards. Yes? parent function. And then from there, we're going to look at the two graphs that they asked us to graph and just look at what transformations I'm doing. So where is that -1 located for g of x? On the inside of the function or the outside of the function? How do I know it's outside? It doesn't have parentheses, or it's not included in the function, which is cubed, right? So what's happening there? What transformation is that doing? Shifting it down 1. So I'm going to take the 3 points that I have on my main graph, and I'm going to shift them down 1. The overall shape of my graph stays the same, okay? I just have to move my points down 1. Alright, on my next one, what's on the outside of my function this time? +1, which means it's going to move it where? Up 1. And then what's on the inside of the function? +2, which is going to move it to the left. So remember, I'm starting with my purple graph, which is my parent graph. So I'm moving all 3 of these points left 2 and then up 1. And again, it has the same shape. Basically, it's like I picked up my graph and just moved it to the new spot. Yes? Now, what if they didn't tell me that my parent function was x cubed? How would I be able to know that that's the graph that I should start with just by looking at the equation? Because there's a cubed on the outside, right? Do I have any other types of like main functions that we can see from there? No, because remember, like our main types of functions were absolute values, square roots, x squared. Those are the types of things you're looking for, and that's going to tell you which one of those it has, what parent function you should use. Does that make sense? Questions on those two graphs? Yes, no, maybe? Alright, so our next type of transformation that we can look at are reflections. So we have two different types of reflections. Reflections over our x-axis, which is when we have a negative on the outside, and reflections across our y-axis, which is when we have reflections going horizontally across our y-axis instead. So across our x-axis is vertically, and across our y-axis is going to be horizontally. And we can think about it the same way we thought about our others, right? If it was on the outside of the function, it moved it up and down, which is why it's going to reflect it vertically, because it's up and down. If it's a negative on the inside, just like with our shape, if it's on the inside, it moves it left and right. So it's going to reflect it left and right. Now, some of our functions we cannot reflect, okay, depending upon what they look like. So if I had an x squared graph, right, it looks like that. Now, if I wanted to reflect that vertically, what would that look like? It would be upside down. So we would look like that. Agreed? But what happens if I try to reflect it horizontally? Why is it going to be the same thing? Because it's symmetrical about my y-axis, right? Or what happens when we square a negative? It becomes positive, so that's why we would end up with the same graph, okay? Versus if we started, say, with our y equals the square root of x graph. It looks like that. So what would we get if we had a negative on the outside of that graph? Which way is it going to point? So it would have reflected it vertically, right? So which way is it going to point now? Down and to the right. So it would be here now. Agreed? Now this one, we can reflect horizontally by adding a negative to the inside. Which way is that one going to point? To the left. Now is it still up? Yeah. So it would look like that. Now how would I make it point down and to the left? A negative on the outside and a negative on the inside. So you have the negative square root of negative x would make it reflect both ways. Does that make sense? Alright. Questions on that? So now, I could ask you a question like we did on the last one where you have to graph it yourself, but the other way that we can ask transformation type questions is by saying, okay, if I give you a graph, can you tell me the equation? Does that make sense? Because sometimes these problems are a little bit faster on like a test or a quiz, but it still is telling me, do you know what it means to be a transformation or not? So this one says, given the graph of f of x equals x to the fourth, which is this first one, okay, find the equations of our next two graphs. So your x to the fourth graph is still a parabola, it's just slightly wider, okay? So it still has a vertex like my x squared graph does at 0, 0. So what's happened on our first graph? It's been reflected vertically, and what else?
It's been shifted
Up by
I can't see the
2. Yeah, it's 2 ticks. So it's been shifted up by 2. So if it's been shifted up, does that go on the inside or the outside of our function? Outside. And if it's been reflected vertically, does that go on the inside or the outside of our function? Outside. So we would say that this is negative x to the fourth plus 2. Are we all okay with that? So then, what's happening to our next one? H of x is what they label it as. It's also been reflected vertically, so we're going to need to add a negative. But then what else has happened? It's been shifted to the right 3 times. So how would I write that? Parentheses x minus, right, 3 here, parentheses to the 4th. So are the parentheses important?
Yes.
Yes, because they tell us is it on the inside or the outside of our function. Questions on either one of those? Alright, so we kind of talked about this a little bit. Okay, so let's compare the graphs. So we're going to look at them in just a second. So what did we say is going to happen for part A? So make sure we're using correct vocabulary. It's going to reflect it across the x-axis.
Yeah.
What about the second one?
It's
It's going to reflect it across the y-axis. And then our third one? Reflected across the x-axis and what did we say our vocab word was? shifted left twice, right? So, making sure that if I ask you to describe the transformations of the functions, we need to use the correct vocabulary, okay? So our graphs should look like that. So the lighter graph is my parent graph. We looked at, okay, here's what happens if I reflect it down. Here's what happens if I reflect it across. And then my last one is we reflected it down, but also shifted it to the left 2 times. Because remember, we can do basically all of these different types of reflections and shifts with one another. Most of the time, we're not just going to have one transformation by itself. It's going to be a combination of several different transformations. So we talked about shifts, up, down, left, right. We talked about reflecting. What's our last type of transformation? We don't rotate things. Yeah, it's when we make it bigger. So we either stretch it or not unstretch. What's another way to say that? Not shrink, not almost, not condense, but compress. So remember, it's either a stretch or a compress. And both of those are what we call our non-rigid transformations. Okay? The reason why they're called non-rigid is because with our left, right, up, and down, it's very clear, right? It's very like, I move up 2 units. I move down 2 units. Pretty straightforward. These ones are slightly different, okay, because it depends on what the number is on how it affects it, okay? So, let's look at a graph. So this is my absolute value graph. Hopefully we recall that from when we did our parent functions. It looks like a V. We have a vertex basically at 0, 0. Now, what do we think happens when we multiply the outside by 3? Other ideas? It opens. It stretches. Okay, so what does that mean by stretches? Does it make it wider or narrower? Wider?
Narrow.
So think about it like slope, right? If this is a slope of 1, agreed? To have a bigger slope means I'm going to get larger, faster, so it's going to be more narrow. Does that make sense? Or we can think about it like if I stretched it up, okay? Going to bring it closer to my y-axis. Agreed? Yeah. So on the opposite end of that, if I have something like 1/3, okay, what's that going to do? It's going to make it wider or compress it away from my y-axis. Does that make sense? We okay with those? Okay. Now, these ones are on the inside. So what do we think these are going to do? It's still going to stretch or compress it, but if it's on the inside, which direction is that going to be now? Instead of vertically, it's horizontally, right? Yes? That's the -8. And then that's the -1/8. The blue one is the -8. And the -1/8 is the green one. So again, it's like horizontally, so we've stretched it out, or stretched it in, basically. We don't see these ones happen quite as often as we do the vertical ones, but they will happen every once in a while. That's why I want you to see it. But the main one that we need to know for sure is the vertical stretch or compression, because we're going to use those a lot on our projects that we have this week. The questions on those. Alright, I did want to look at one last example. Alright, so let's say I have a graph. And, it's a quadratic graph. And I told you that this point is at 2, 3. Okay? What would my equation for that graph be? So f of x equals, it's going to have an x squared, right? Because it's a parabola, so that's my parent graph. So it's going to be a parentheses. How far to the right have we moved it? 3. So it's going to be x minus 3 squared, right? And then how far up have we moved it? Oh, sorry, those are
It's the
opposite.
opposite.
There we go. 2, 3. Are we okay with that? But now, how do we know if it's been stretched or compressed? We don't unless they give us what? Not another graph, but another point on our graph. So let's say that this was at 1, comma, so 5. Okay? So basically we're trying to figure out, okay, what A value, right, is in the front, or how far has it been stretched or compressed? Agreed? So how would I figure that out? Math, okay. So if I have a point, what does a point represent? Well, like, the 1 would be my what value? The 5 would be my y value. If I have an equation with an x and a y, what can I do with my 1 and my 5? Plug them in. So 5 equals a times 1 minus 2 squared. Well, now, how many variables do I have left? Just 1, the a. So we can solve, agreed?
Yeah.
So I would subtract my 3, and we get 2. And then, hold on a second, guys. -1 minus 2 gives us -1 squared is just 1. So I get a equals 2. So what would be my overall function? 2 times x minus 2. Okay. You're going to need to be able to do that, okay, with different types of functions. I need to be able to take 2 points, okay, and figure out how far has my graph been stretched or compressed given a parent function. Okay?